So let me get these notes passed out. There is no homework worksheet that goes along with these today. So basically, today is just practice with our transformations and things. Chromebook should be put away.
Miss Wilson, you have earned a snack card.
Oh, I got it first try. I didn't get it finished try my first time. I'm gonna get on my level.
What are you doing?
Stop cheating. You say that, but you're still trying because you can't. I don't know. You probably have to because you don't have it right now.
All right. So properties of transformations. So first thing that we're going to talk about is just a couple of vocab words here, and then we're going to get into talking about what transformations are affected by these couple of vocab words. So the first one is congruency. Chromebook should be away. Congruency. If a transformation produces an image with the same size or same shape and size as the pre-image, then the figures are congruent. So the word congruent basically means equal. All right, so when you do something, so like, for example, up, down, left, right, that does not change the shape or the size of the figure. So those two figures would still be congruent. A reflection, all it does is reflect the exact same shape, which doesn't change the size or the shape of the figure, so that's still a congruent figure, okay? But a rotation, does that change the size or shape?
No, not really.
No. So that's still a congruent. What about a dilation? It changes the size, right? A dilation would make it bigger or smaller, so they would not be congruent. One thing that you need to know, and this symbol is important, congruency. That symbol is an equal sign with a little like squiggle at the top, means two figures are congruent. So a congruency statement for the triangle shown might be that triangle, so triangle ABC is congruent to triangle A prime, B prime, C prime. So that's how you would write a statement showing that those two figures are congruent. The little triangle symbol means it's a triangle, obviously. And then the equal with the squiggle on top means that they're congruent, that they're still of equal size and shape. Yep.
Why didn't we need the little squiggle?
Because if we didn't, then we would say that they're exactly equal. And they're not exactly equal because they're not exactly in the exact same spot. But their size and shape are still equal, just their location is not. So that's why it's congruent. That means estimation. So squiggly equal sign means estimation.
And an equal sign with a dash for it means it does not.
Correct. All right, so basically a congruent is going to be our up, down, left, right, our reflections, and our rotations. The size and shape are still the same with those. Now, when it does change the size or shape, that's when they're no longer congruent. And that's called when they're similar. So similarity, if a transformation produces an image with proportional size and congruent angles, these figures are said to be similar. So proportional size just means that the ratio in the side lengths is the same all the way around that triangle. Okay, so that's what proportional means. That if I took a ratio, like if this side's 2 and this side's 4, that's a ratio of 1/2. So these sides would be a ratio of 1/2, and these sides would be a ratio of 1/2. It just means that they're all like reduced by the same amount or enlarged by the same amount. Reckon if I have to walk over there, you're ready. What's here?
What would be determined if they both change shape and size?
Well, they both wouldn't change shape and size.
So you can't change shape and size?
Well, we're not really going to change the shape per se. Right now we're only going to change the size. And the symbol for similarity is just the squiggle without the equal sign. So if I was going to talk about these two triangles, I would say that triangle ABC is similar to triangle A prime, B prime, C prime. So that just means that basically one shape was made from the other. The angles are still the same, but the side lengths aren't, which just makes them similar. Congruent is when they're still the same size and shape. So basically this is only going to happen with dilations. Translations are up, down, left, right.
Yeah, but you didn't write translation.
I just but some people don't know that translations are up, down, left, right. Well, some do. All right, moving on to the examples of what we're going to do with this. So these two questions down here say describe the transformation that was happening in the shape. What do you notice about corresponding lengths and angles? So are they still congruent or are they just similar? And how would you write your similarity or congruent statement? So looking at these two figures on number 1, would you say it went up, down, left, right, a rotation, a reflection, or a dilation?
Reflection.
A reflection, and it's a reflection over the x or the y-axis. The y-axis, because right here is the original image, and then it looks like it was just flipped to be that image, so it is a reflection over the y, so I just put reflect the y-axis. Now, with a reflection, the size and shape do not change. So would you agree that this is a congruent or a similar? Congruent. This is congruent because the size and the shape, the size and the shape did not change in size. Size and shape. So it says, what do you notice about corresponding side lengths and angles? You could say that the sides and the angles are congruent. And they're congruent because they're still the same size. That's what makes them congruent. It's still the same shape and size. And then it says, write a similarity or congruency statement. So that just means now you're going to say triangle ABC is congruent to triangle A prime, B prime, C prime. So triangle ABC is congruent, so that's the equal sign with the squiggle on top, to triangle A prime, B prime, C prime. Yes, Karen.
I know we're not on 2 yet, but
We'll wait till we get there. Wait till we get there.
it's not.
So are there any questions on number 1? Okay, all right, well, let's look at number 2. So it says, describe the transformation. So remember, the one without the primes is the original, the one with the primes is the new one. So would you all say that this is an up, down, left, right, or reflection, or rotation, or dilation? Dilation. And did it get bigger or smaller? Bigger. It got bigger. And it got bigger because look at the labels. The small one is ABC. The big one is A prime, B prime, C prime. The prime one's the new one. So it's a dilation. And we're going to have to talk about what type of dilation it is. So it's a dilation by what number? And we talked about last week how to find that dilation, that scale factor. So I take the ratio of the new one to the old one. And I only want to use a straight line. So when I look at the bottom here, A to C is 2. But A prime to C prime is 6. So I take the ratio of the new one, which is 6, to the old one, which is 2, and 6 over 2 is 3. So it's a dilation by 3, by a scale factor of 3, which makes sense because it got larger, and we talked about how scale factors, if it's over 1, it makes it larger, less than 1, smaller. So we okay on finding that dilation? Yes.
What happens if the scale factor is 0? Well, like, what is the scale factor is 0? Smaller than 0.
But it's still, the 3 would still tell us that it got larger because
3
it's over
times
1.
0 is 0.
Okay, all right, B, it says, what do you notice about corresponding side lengths and angles? Well, I know that they're going to be similar because the size is not the same. So the side lengths, if we go back up here to the top, if it's a similarity, a transformation produces an image with proportional size and congruent angles, means that it's similar. So I will put on here, since I know that they're similar, that it's only proportional sides and congruent angles. The angles don't really change just because the side lengths changed. Okay? The angles are still the same, even though side lengths are different. So the way I would write that is triangle ABC is similar to triangle A prime, B prime, C. And I was fighting with the Math 7 kids about why angles have different, we were talking about how a triangle adds to 180 degrees. And it says that if a triangle adds to 180 degrees, then it could be more than one triangle. And it's because angles can still be the same, even if the side lengths are different.
We never learned that.
You all
Yeah,
learned
we-
that last year.
No, we did.
No, we did
Yes,
not.
we
I
did.
hate shapes. Not that shapes.
All right, so moving on to here. So we're going to do some graphing practice. So it says, use the figure below and follow the steps of the table. Include an algebraic representation of each transformation. And for size, state whether the image is congruent or similar. And for orientation, whether it stayed the same or changed. So remember, size is the exact same size, so it's either congruent or similar. Congruent would be exactly the same size, similar would be that it changed size. When it talks about orientation, that's talking about which way it faces. So if one triangle's this way and the other one's this way, that's a change. But if they're still both facing the same way, that's the same. Okay? You probably need your paper with your 4 little boxes on it right now.
Never answered my question about.
Okay, what answer? Oh, they go over here.
Can you like reflect this triangle at you? Kind of like.
Right, but if you reflect it over the y-axis, it will be the same shape, just like C would be here, A would be here. If you reflect it over the x-axis, it will be
All right, so the first transformation, I'll do this one in blue. 11 units left and 1 unit up. All right, so I'm going to take my ABC and I'm going to shift all 3 points, 11 left, 1 up. 1, 2, 3, 4, 5, 6, 7. The A prime. It's so hard to look at this one. That's why I usually sit down and graph. It's a lot easier. So graph it with me, and then we're going to fill in the chart together.
Let's do a triangle then.
All right, so hopefully we're there with our graph. So algebra representation, algebraic representation. When I move it left and right, what value does it affect? X. When I move it up and down, it affects the Y. So 11 units left would be X minus 11, and 1 unit up would be Y plus 1. So that would be my algebraic representation. I moved it left 11, up 1. Now, did the size stay the same or did it change? It stayed the same. So it says in there, it says whether the image is congruent or similar. So since it stayed the same size, it's congruent. And did the orientation of the figure stay the same or change? The same, still facing the same way. All right, so the second one says that we're going to reflect the new image, so we're not going back to the old one, the new image over the x-axis. So this ABC, this blue one, is going to flip over the x-axis. So remember to do a reflection on a graph. You count how far away the points are from that x-axis, and they count the same. So if you forgot, I'd watch. So I'm going to start with A here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's my A double prime. That's the second new image. If I do B, 1, 2, 1, 2. Then C, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so you can look at your little paper with the squares on it, and it says when you do a reflection over the x-axis, what does that do to the values, the x and y values? The y becomes negative. So x comma negative y, which makes sense because this b is at -6, -2, and now it's at -6, +2. So the y changed. All right, would you say that these sides of these shapes are still congruent? Yes, they're still the exact same size. So I'm going to put congruent in there, so I'm just going to abbreviate it. And would you say the orientation stayed the same or changed? Changed, because it's not facing the same way anymore. This one's upside down.
A triple prime.
Mm-hmm. All right. The third one says to rotate the new image 90 degrees clockwise. So what does it say on your squares about rotating something on 90-degree clockwise? What happens?
They switch.
They switch, and x becomes negative. So they switch, and the x becomes negative. So when I go up here, what I would do if I have to graph a rotation is I would find the ordered pairs first, is what I would do. So I know that this is at -10, 8. I know that this one's at -2, 8. And this one's at -6, 2. So I'm going to switch them and make the x become opposite. So when I switch these, what would the new ordered pair be?
8,
8, 10. This one would be
8, 2.
8, 2, because I'm switching them and the x is becoming opposite. And this one,
2, 7.
2, 6. So that'll help me graph my rotation. So I just switched them and the x became positive. So 2, 6 would be right here. So that would be my B triple prime. My A would be at 8, 10, so 8, 10. So that would be my A triple prime. And then my C, 8, 2, and that would be my C triple prime. All right, you got a question? Well, hopefully everybody knows where their little paper is with the 4 things. It's going to be super helpful. All right, would you say that the size stayed the same or changed? Same size still, so still a same congruent size. And would the orientation stay the same or change? Change. Because this kind of goes on its side. All right, last one on there, like this. So this one says dilate the new image. So the new image, by a scale factor of 0.5. So remember when I do scale factors, I always multiply the x and the y by that 0.5. So I'm going to take these 3 points of that new figure, and I'm going to multiply them by 0.5. So that was good that we went ahead and put those on there, because now I can just multiply them. 0.5 is the same thing as about a hat. It's not about a hat. It is 1 hat. All right, so this new figure, instead of being at 8, 10, it's going to be where? 4, 5. Because I'm multiplying 8 by a half and 10 by a half. So that's going to be at 4, 5. So 4, 5. 4, 5. So right there. So that's going to be my A double or quadruple prime. Whoa. We're getting on a lot of primes here. It's not good. All right, what about C? C was at 8, 2, so if I take half of that, it would be at 4, 1. And that's going to be my C quadruple prime, so 4, 1. So there's my C. And then what about my A? My B is at 2, 6, and it would be at 1, 3. So 1, 3. And that's my B quadruple.
I got this one.
Oh, a lot of primes.
It's kind of a bit too much. I think our universes have been.
All right, size. Are they congruent size or are they similar size? Similar size. Because they're no longer the exact same size anymore. Now, from the red one to the purple one, did it stay the same orientation or change? Same. It stayed the same from the red to the purple. The orientation is still facing the same way. It just changed size. Is this like way over our heads, or are we just tired?
We are super tired.
That's what I'm saying, Mom.
I got 2 minutes.
All right, I'm gonna give you all a chance right now. Okay, to talk about. It says the example show an image after a series of 2 transformations. Identify the 2 transformations that took place. So here's your original. Here's your new. Here's your original. Here's your new. Here's your original. Here's your new. Talk about what happened. Let me give you a second. It says that there's 2 transformations for each one.
What?
So did it go up 3 and down 5? Did it have a reflection over the x-axis? And then reflection of the x-axis and then a dilation of 3? Like, talk about the 2 transformation that it has.
On the test?
It could be.
What did you make?
I think she just killed her.
All right, shh, shh.
Are we just naming or are we saying how they?
You're telling me how they moved. So, like, did they go a reflection over the y-axis, and then up 3? Did they rotate by 90 degrees and then go up 3? Like,
Is there any rotation?
One. Let's do the best you can.
Wait, not 7 so circumference?
Or sorry, circumference.
We never did circumference.
No, do them all.
That's reflected. We have to say like up 7, down 7. Wait, up 7.
so when I looked at number 4, I started to think to myself, okay, well, it couldn't just go down and left, because that would, look at the shape, okay, the orientation, I mean. So the orientation changed. So for orientation to change, it either had to be one of 2 things. A reflection or a rotation, okay? So the dilation would change size. So I thought, okay, what if I reflect it over the y-axis? Okay, so that's where I started. So I said, okay, I reflect it over the y-axis. So it would look something like this. Okay, I'm getting there. I just made a rough shape there. I didn't really have anything. And then after that, after I reflect it over, what do I think maybe happened?
Something.
It went down, and if you want to be extra precise here, look, 1, 2, 3, 1, 2, 3. What's that? 5, 5, and then 1, 2, 3, 1, 2, 3. So my shape is right here. So if I shift it down, look where it's going to be. I'm also going to have to shift it where? Right. So I'm actually going to have to go down and right. So I'm going to have to go down, and then if I come to this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then right 1. So I guess I won't actually have 3.
No, because that's just one translation. Yeah.
Down 9, right 1?
Yeah, isn't that just one translation?
I think it's 2.
All right, number 5. Well, what do we think here? A rotation?
I didn't even get the other time.
Yeah, it's a rotation.
It's a rotation because of the shape there, okay? And then what? The one on the left too? Okay. All right, so I would rotate this. Well, this is 90, so this would be 180. So rotate 180. And when you rotate 180, that just changes the x and the y sign. So if this one is at 3, 1, My other one's gonna be -3, -1. So it's like right here. So it looks like after I rotate, I still have to go left 2, down 1. And if you want to be like super precise, then you could actually move the whole figure. It didn't tell us that we had to graph it though, so that's why I'm kind of just doing it like more verbally or just with one point. So what I did again, after I rotated it 180 to be in this quadrant, I thought to myself, okay, I know that since this is 3, 1, a rotation of 180 changes the sign of the x and y. That's what it says on your paper. So 3, 1 is -3, -1. So I graph -3, -1, which is not on top of this one. So in order to get it over here, I would have to move it left 2, down 1 to get it right there. So that's how I need to do that. Once again, it's all on your gray paper. All right, and then the last one. It's obviously a what? It's obviously a dilation. Okay, and I know it's a dilation because it got bigger. So let's count. 1, 2, 1, 2, 3, 4. So I do new over old. So that's 2. So dilation by 2. And then what?
Some more translation.
And then some sort of translation. So it got bigger. So if this shape got bigger, like up here, so like this point right here is at -2, 2. So that would have made it be at -4, 4. And then it moved. 1, 2, 3, 4, 5, 6, 7. So it looks like a right 7. And then down 1, 2. So I guess you're right here, and they are counting translations as 1. The right 7 down 2. Mine says, that's not that right. No, I was looking at.
Maybe on the, yeah, I think it is.
So that point would be at -2, 2, and then I have to. Oh, Miss Wilson's a dingleberry gumbat. Okay, look. Real quick. This dingleberry, what point is this? -1, 2. -1, 2. So that would be a -2, 4. So I counted that wrong because I did my point wrong. So it's actually a 1, 2, 3, 4, 5, 1, 2. What I did for counting the point wrong. Everybody makes mistakes. Everybody has those days.
I didn't even get to 5.